Okay, so we're going to look at how spheres can pack together in a crystalline lattice. The crystalline lattice is just the regular arrangement of atoms within a crystalline solid. And those atoms are going to arrange themselves so that they are at a minimum energy. To think about these three-dimensional arrangements, we're going to talk about a unit cell. So that's the smallest unit of the crystal that if we took it and repeated it in 3 dimensions, we could reproduce the entire crystal lattice. Okay, so this is a 2-dimensional example. So like floor tiles, right? So if this was a floor tile and you repeated it over and over, you would get this overall pattern, right? Now that might not be what you would, go for at first. I think it's more instinctual to not be chopping all the circles into pieces. But this is the smallest square that you can repeat and get the overall pattern. So that's what we're calling the unit cell. These circles represent the lattice points, which would be occupied by the atom, ion, or molecule. Any questions yet? There's lots of different types of unit cells. We are going to look at cubic unit cells. So as the name suggests, these are cubes. The edge lengths are all the same, and the angles are all right angles, 90 degrees. There's a whole bunch of other types of unit cells, but we're not going there. So when we're looking at these unit cells, there's going to be different colored spheres or balls. Those all represent the same element. It's just a different color so that we can see what's happening a little better. It's kind of hard to see 3-dimensional stuff on a 2-dimensional screen. And 2 things that we can measure about these different unit cells is the coordination number and the packing efficiency. So coordination number is the number of atoms that each atom is touching in this structure, in direct contact. And that's important because the atoms that get close to each other like that are going to interact more strongly than atoms that are further apart. The other thing that's measured is packing efficiency, and that's just the percentage of the volume of the cell that's actually occupied by the spheres. If you have a higher coordination number, you generally have a higher packing efficiency. So these are the 3 cubic unit cells and all the information. But let's look at them one at a time. So this is the simple cubic unit cell. And so what we have here is a cube, and at the corner of each cube is the center of an atom. Okay? So the atoms are going to touch along the edges. So if the radius of one of these atoms is r, then the length of an edge is 2 r's, right? 2 times r. So the edge length for this is 2 times r. And this unit cell contains the equivalent of 1 atom. So if this was, made out of styrofoam or something that we could manipulate, note to self, get something like that. We could pull these apart and put them back together and see that these pieces could fit together and make one complete sphere. Because each of these is 1/8 of an atom. So here's an 1/8, and then you go around the back, there's an 1/8, and then you come out here, there's another 1/8, and around this way, there's another 1/8. So that's 4, and then the same guys underneath. So this is looking at the spheres complete. And the unit cell is going from the center of these to each other. The packing efficiency is how many spheres each is touching. So here, looking at this guy on the corner, well, he's touching the one above and the one next to it and the one behind, right? So that's 1, 2, 3. And then there's one on this side, 4, one in front, 5, and one underneath, 6. So a coordination number of 6. The packing efficiency is 52%. So packing efficiency can be calculated. Here we're going to look at a two-dimensional lattice because it's easier to think about. And it says calculate the packing efficiency. So here's our unit cell. And packing efficiency is going to be the volume of the spheres divided by total volume of unit cell times 100. Okay, so this isn't volume, right? Because this is two-dimensional. So sorry, I'm messing up your notes. So this is going to be area, the area of the circles divided by the total area of the unit cell. So looking at this white square, how many circles are represented? Not how many pieces of circles, but if we took the pieces of circles that are in this box and put them together, how many circles could we make? One, right? Because this part right here is 1/4 of the whole circle. This is 1/4. And we have 4 of those, and 4 times a fourth is 1. So that's exactly what we were talking about with the cubic unit cell and the corners being 1/8. It's just a lot harder to see in 3 dimensions. So we have one circle, and what's the area of the circle? What's the area of any circle? Pi r squared. We don't know what the radius is. It's okay. What's the area of this square? Well, it's the length times the width, right? How long is an edge? 2r. So the cell has an area of 2L times 2L, right? Or 4, sorry, R's, those are R's. It would be L times L, or 2R times 2R, which is 4R squared. So the area of the circles in that unit cell, pi r squared. The area of the whole thing is 4r squared. And we don't know what r is, but that's okay because the r squareds cancel out. So it's pi divided by 4 times 100. So 78.5%. So in this unit cell, 78.5% of the area is occupied by the purple circles, and the remaining percentage is empty. And that's true whether you're looking at this square or at a much bigger area, the packing efficiency is the same. Any questions? The next unit cell is called the body-centered cubic unit cell. So we can think about this as like, okay, here are the purple pieces from that simple cubic unit cell. And they're spread apart a little bit so that one atom fits in the center of this. It's centered in the body of the unit. Finding the edge length is a little more complicated now because they don't touch along the edge. They're touching from this corner diagonally to that corner. So if you like geometry, there it is, but this is the edge length right down here. And this is not something, again, that you need to memorize. If there's a question on the exam where you need that number, it will be given, that equation, it'll be given to you. So this edge is equal to 4 times the radius divided by the square root of 3. This is the picture we were just looking at. So this cell has 2 atoms in it, right? We have the 8 eighths, plus the 1 in the middle that's completely in the unit. This is what it looks like without chopping off all the extra pieces. This is trying to represent how many atoms it's touching. And remember, this gold atom is the same element as the purple ones. We're just making it a different color so we can see it easier. But here, the coordination number is 8. If that doesn't make sense to you, that's okay. Packing efficiency is 68%. It's higher. So there's a bunch of different calculations that can be done. Here, an atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? Well, in case we forgot, there is the edge length. L equals 4r over the square root of 3. That's not what I wanted. That's not what I wanted either. Okay. L is equal to 4r divided by the square root of 3. So we're given one number, radius of 138 picometers. So r is 138 picometers. And what are they asking us to find? Volume, that's not what I meant to do either. There we go. Volume in cubic centimeters. So we're starting off with picometers. We can convert picometers to centimeters and then find the volume, or we can find the volume in cubic picometers and then convert to cubic centimeters. That sounds not as fun. So let's convert this to centimeters before we get into it. So I can convert to meters by simply writing what pico means. Anybody know what pico means? Times 10 to the minus 12. So after you get out of deci and centi, it's all multiples of 3, right? Nano is minus 9, because nano and 9 are similar, right? And so this is the next smaller one, 9 to 12, so negative 12 meters, and then we can convert to centimeters. 1 centimeter is 1 times 10 to the minus 2 meters. So 138 EE minus 12 divided by 1 EE minus 2 is 1.38 times 10 to the minus 8 centimeters. Yes?
How'd you get 10 to the negative 2?
So centi means 10 to the minus 2.
Okay,
We want centimeters. Mm-hmm. Yeah. Now, my calculator showed me 0.000, bunch of zeros, 14. Does that mean I should round this? No. It's just that the calculator is trying to show it to me in decimal notation because that's the mode it's set in. And it can do it just kind of. It can show me 2 of the digits. And so it's doing that. But I need to be smarter than my calculator and recognize, oh yeah, it's rounding because it didn't have enough room on the display. So that is r. So then we can figure out the length of a side of this cube, right? This is 4 times that radius. Divided by the square root of 3. Just had an argument with my calculator. So 3.2 times 10 to the minus 8 centimeters. So we're talking about a cubic unit cell. So that's a cube, and the sides are L in length. So then the volume is L cubed. 3.2 times 10 to the minus 8 centimeters cubed. Which gives me 3 point, wait a minute here. Yeah, I thought my calculator was cheating on me. That's actually 3.1869. That looks better. So 3.24 times 10 to the minus 23rd cubic centimeters. That's really tiny, but it should be really tiny. The body-centered cubic unit cell has a total of 2 atoms in it. It should be really, really tiny. Any questions? The third one is a face-centered cubic unit cell. And again, these purple ones are the corners of that original unit cell. And now we're spreading them out a little bit. And on the face of this cube, an atom is centered. So it's face-centered. So half of it is in the cell and half of it is not in the cell. And on the top face, the same thing. And this face, and the back face, and this face over there, and the bottom face. Each face has half of an atom in it. So we have 1, 2, 3, 4, 5, 6 of those, right? So we have 6 half atoms plus 8 1/8 atoms. So a total of 4 atoms in there. The geometry is a little simpler than the cubic, than the body-centered. Here they're touching along the diagonal of the face. So we end up with this guy down here. Sometimes that is misunderstood. The r is not inside the square root. I know it kind of looks like that, but you could think of it as 2r times the square root of 2, same thing. That'll come up in a homework problem. Here's looking at the entire thing. Now it's like, wow, that's just getting a little hard to look at, right? And here, looking at how many that's directly touching, I couldn't look at that and tell you. But hey, it's 12. They did that for us. The packing efficiency is 74%. So this is a fun problem that could show up, homework. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of chromium. What? I'm not going to do the problem. It takes a while. Can we calculate the volume of this unit cell? Yeah, we just did that, right? So you can calculate the volume of the cell in cubic centimeters. Well, that's the denominator part that you want, right? Because density is mass divided by volume. So there's your volume. You're going to calculate that like we just did in the previous problem. How do we find the mass of this cell? A body-centered cubic unit cell has how many atoms in it? 2. 2 atoms. Well, how much does 2 chromium atoms weigh? So we can look over here, and it's going to give us the molar mass, 52.00 grams per mole of atoms. But we have 2 atoms, right? So 2 atoms, and I want to convert that to moles and then to grams. What number do I use to convert between moles and atoms? Avogadro's number. And then this is the molar mass. And we're going to come up with a mass in grams that's really, really small. And that is going to be equal to the mass. So that's equal to the mass. You take that mass, you divide by the volume, and it comes out to be 7.18 grams per cubic centimeter. This is a much more reasonable, final exam question. How many atoms are in the unit cell in the face-centered cubic structure? I heard a little tiny 4, which is correct. The face-centered, the cube has 6 faces, right? There's half of an atom on each face, so that's a total of 3 atoms. And then there's atoms at all the corners, 1/8 of an atom. So that's another atom, so 3 plus 1 is 4. This would be the simple cubic unit cell. This would be the body-centered unit cell. We can also look at crystal structures by thinking about the layers of atoms. Like if you're building this solid up, how would the layers be lined up? Well, this is the simple cubic structure, and what we have here are atoms laid out in rows. Oh, that's not very good at all. And they're all lined up on a grid, right? That's not the most efficient way to pack spheres together, but that's what they're doing. So the bottom layer looks like that. The next layer is sitting right on top of the first layer. That's actually really hard to do. You got ping pong balls or marbles or something, you want to try that at home. Because those marbles want to fall into this little indentation caused by the 3 balls below it. So this has a lot of empty space. In closest packed structures, which as the name suggests are more closely packed, the layers are going to look like this. So here we have a row of atoms, but the second row of atoms is offset by half an atom so that they can squeeze together better here. And then this one will match up with this one and this one over here. So the bottom layer is more closely packed, and then we can look at how are those stacked on top of each other. Well, we're going for closest pack, so we don't want them directly on top of each other. The next layer is going to be offset, just like this row is offset from the first row. So this is going to sit in the indentation caused by the 3 atoms below it. So there's 2 ways you can stack these sorts of layers. They have the same packing efficiency and same coordination number. They're just a little different in how the 3rd layer is aligned. What's called hexagonal closest packing, you have layer A and layer B, and then layer A lines up directly, the 3rd layer lines up directly with layer A. So we have an AB pattern. The unit cell here is not cubic, it's actually hexagonal. So here's the unit cell. That's the smallest that contains a representation. And the angles here are 60 and 120 instead of 90 degrees. And so if you took this whole thing and cut it all up, you can see where the hexagon comes from. Right? You can also do this in a way that gives you a cubic unit cell. So bottom layer A, second layer B. Now the 3rd layer is not directly on top of layer A, it's offset also. So instead of having that ball in the front where it would line up with this one, it's lining up with the back. So this is known as an ABC pattern. And this happens to be exactly the same as the face-centered cubic unit cell. So just try to go here with me. So here's our first layer. The second layer is offset. The 3rd layer is offset compared to both of these. And then the 4th layer is finally the same as this one. So A, B, C, and this would be A again. So we're going to put those guys together and tip them on their side and then cut into them like this. And then we can see, oh yeah, that's a cubic, a face-centered unit cell, right? Because we have an atom centered on each of the faces.